Hey guys, and welcome back to another video on the channel. In today's video we're going to be evaluating another MIT integral B qualifying integral. But this integral is going to be, well, it looks a bit harder than the one we last did. But yeah, let's just take a look at this example. So it's the integral from 0 to 1 of the infinite product, so capital Pi, from k equals 0 to infinity of 1 over 1 plus x to the 2 to the power of k. So this is 2 and there's power of k, so I'm just going to move that down a bit. 2 to the power of k dx. Okay, so what makes this integral so hard is probably this thing in the middle. It looks terrifying. However, we just need to understand what it's saying. So this is an infinite product. So if you have a sum, so if I go sum from I equals 0 to I equals n of, let's go I, that just means 0 plus the next number after that, so 1 plus 2 plus ... all the way up to n. Okay. With an infinite product, it's the exact same idea. So I equals 0 to infinity. This just means 0 times by 1 times by 2, etc. But this whole thing would be 0 because the first term is 0. So all we got to do is pretty much try and work out what this middle bit here would be first, pretty much, before even integrating it at all. Okay, so first of all, let's just copy and paste this guy here. So just go copy this guy, copy, and then chuck him here and break him down. Okay, so the index is this k here. Now that is only getting plugged into here. So if you were to evaluate this, or start to evaluate, you would start to get something like this: 1 over 1 plus x 2 to the power of 0 plus, or not plus times, sorry, so brackets, times 1 over 1 plus x to the 2 to the power of 1 times by 1 over 1 plus x 2 to the power of 2, etc. And then 1, I'll do one more and then I'll do a bunch of dots, x 2 to the power of 3, and then that goes on pretty much forever. Okay. What we want to do is we want to start evaluating these terms here and see what we start to get. So if you did this forever, what you're going to get is pretty much, well, the exact same thing. So 1 over 1 plus, and this would be x, 2 to the power of 0 is just 1, so just 1. So times by 1 over 1 plus x 2 to the power of 1 is just 2, so just 2. Times by 1 over 1 plus 2 to the power of 2 is just going to be 2 squared, so that's going to be 4, so 4. And then if you keep doing this, you start to see a bit of a pattern pretty much. So all the powers start to pretty much double. So if you look at pretty much this power, so 1 times by 2 gives you 2, 2 times by 2 gives you 4, and then 2 times by 4 gives you 8, etc. And imagine this continues forever, okay? Now multiplying fractions is quite easy. It's just top times top, and then bottom times bottom. But if you did this infinitely, it's going to be quite hard. So all we want to care about is pretty much the bottom bit, because do you agree? 1 times 1 times 1 times 1 is just going to be 1. It's not going to change at all. So the top of this fraction remains the same. The bottom bit, though, we can just rewrite it like this. So 1 plus x times by 1 plus x squared, and then 1 plus x to the power of 4, and then 1 plus x to the power of 8, and this continues on indefinitely. Okay, let's start evaluating these and see if we can find any pattern pretty much. Okay, so 1 plus x times by 1 plus x squared. So what you're going to do is FOIL that, so multiply this term by this, and multiply this by this, and see what we get. So 1 times by 1 gives you 1, and then 1 times by x squared gives you x squared. X times by 1 gives you x, and then x times by x squared gives you x cubed. Okay, so what we get is pretty much, well, 1 plus x squared plus x cubed. Okay, now let's add in the next term. So 1 plus x times by 1 plus x squared times by 1 plus x to the 4. Okay, now this would be the exact same as timesing this guy here. So this by the 1 plus x to the power of 4. So this is the same as this. So that means this should be the same as this. Okay? So what we can do is just evaluate this. So where we do that is just FOIL it again. So we can go 1 times by 1 and times by x to the 4. And you just do that for each term. Now the way I'm going to do it is I'm going to break it up pretty much because you've got a lot of terms in the first brackets here. So I'll just write it as, alright, first term times by this. So 1 times by 1 plus x to the 4 plus x times by 1 plus x to the 4 plus x squared times by 1 plus x to the 4 plus x cubed times by 1 plus x to the 4, and distribute this. So this is going to be 1 plus x to the 4 plus x to the 5 plus x squared plus x to the 6 plus x cubed plus x to the power of 7. So if I rearrange that, I get 1 plus x squared. Let's move to the side, we're about to run out of room. Plus x cubed plus x to the 4 plus x to the 5. Move to the side. Plus x to the 6 plus x to the 7. Now, if you actually keep doing this, if you did this indefinitely, so if you go 1 plus x times by 1 plus x squared times by 1 plus x to the 4 and then 1 plus x to the 8, and you kept doing that indefinitely, what you're going to get is this thing, but it's going to be leading powers pretty much. So what we have pretty much is the powers of x are increasing by a degree of 1. So if you did this indefinitely, this would be plus x to the 8 plus dot 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 plus x to the n. So whatever term you stop at, but it'd be infinity. Okay. We can rewrite this as a sum. Okay. This green bit is the sum starting from n equals 0 to infinity of x to the power of n. Because you agree, if I were to evaluate this, this would be x to the 0 plus x to the 1 plus x squared plus x cubed, etc. Because x to the 0 is 1. So it's exactly, I should probably highlight this green, it's exactly the same as that pretty much, okay? So what does this mean pretty much? So what this means is the product. Now remember, we're taking the reciprocal. We've only taken the bottom half of it, okay? We didn't care about the top at the moment. So we've taken the reciprocal, so it's a different product. So the product from k equals, what do we say, 0 to infinity, and it's the reciprocal, so it's just 1 plus x to the 2 to the power of k, is the same as the sum from n equals 0 to infinity as x to the n. Okay, we've made that thing there. Now if we take a look further at this sum here, we can see if we were to write this as a sequence, 1 x squared, x cubed, since it's increasing by x, this is clearly a geometric sequence. It's getting times by x each time. Okay, so this must be a sum of a geometric sequence, an infinite sum. Now we can evaluate this if we assume x is smaller than 1. So we know this is a geometric sequence, so geometric sequence, and we assume, so it's important, we assume x, well the absolute value of x is smaller than 1, because r is your ratio, which is x. Okay. Now, if you want to work out the sum of a geometric sequence, and you don't know the formula, let me just pull it up very quickly. I can't remember the formula off the top of my head all the time. It would be s infinity, your first term, so equal to your first term of 1 minus r. Now in this sequence here, your first term is 1, so t of 1 is 1 and r is x. Okay, so what we can do is just chuck this guy into here, and we can chuck this guy into here. Okay, so the sum from n equals 0 to infinity of x to the n is equal to the sum of a geometric sequence infinitely if r is less than 1. So we're just saying r is less than 1, so that means x must be less than 1, of 1 over 1 minus x. Okay? So that means is if x is less than 1, this crazy thing here, the reciprocal of this, is just equal to this thing here. That's kind of mind-blowing, not gonna lie. But, so we've made that connection there. Now remember, we looked at the reciprocal, so we're trying to evaluate this guy here. So the integral from 0 to 1 of the infinite product, k equals 0 to infinity, of 1 over 1 plus x 2 to the power of k dx. So this must be equal to 0 to 1 of 1 over this whole thing. So 1 over 1 minus x dx. We can tip and times this thing. So we can rewrite this as the integral from 0 to 1 of 1 minus x dx. So we took something very scary and we transformed it into a very easy thing to evaluate. This we can just use the power rule. So this would just be x minus x squared on 2, evaluated from 0 to 1. Plug in 1 first, so you get 1 minus 1 squared minus 0, because that next term would be 0. 1 minus 1 squared over 2 is just 1 minus a half, so the correct answer is a half. So this crazy integral at the top here is just equal to a half. Ta-da! So that's an MIT integral qualifying question for the integral B. I hope you enjoyed this video. If you did, leave something in the comments and like and subscribe, and I'll see you in the next one.